All right. You ready, everybody? Today we're going to be doing section 3.3. Welcome back. Today's section is on finding the zeros of quadratic functions. Let me pull up the slides and we will get started. Here we go. Okay, so let's take a look at an overview. Oop, come on. There we go. So first, we're going to start by defining quadratic functions and equations, kind of building off what we talked about in the last section. We'll talk about finding the zeros of these functions by factoring. Then we're going to revisit the process of completing the square, and we're going to generalize it a little bit more. Then we'll talk about how you can find zeros of these quadratic functions by completing the square. Then we're actually going to derive the quadratic formula, everybody's favorite, right? Then we're going to see how to find zeros using the quadratic formula. And then we'll finish up by talking about the discriminant of a quadratic polynomial. The discriminant is actually really helpful because it characterizes the zeros of a quadratic function and kind of tells you how many you'll have and what they're going to be like. So it's really handy in that way. Let's go on here. So what is a quadratic function? A quadratic function is a function of this form here, where this is just a quadratic polynomial, and the leading coefficient here is not zero. You need this squared term there for this to be a quadratic function. Then what is a quadratic equation? Well, a quadratic equation is just an equation of this form where you have a quadratic polynomial set equal to zero. Make sure a is not zero, so that way you actually have this square term there. And the big idea for this section is right here in the box. So solving this equation here for x is the same as finding the zeros of a quadratic function. It's the same thing. And this is literally a root finding problem, which is what we talked about in the previous section. So today we're essentially looking at a very specific kind of root finding problem, finding the roots of a quadratic equation, or equivalently, finding the zeros of a quadratic function. So that's what the whole lesson is about today. All right. So there are three ways that you can solve and find the roots of this equation. One is by factoring, and the efficacy of that method depends on the factorization domain, which we talked about previously. You could use completing the square. Completing the square will always work. You can always solve a quadratic equation using completing the square, and the quadratic formula will always work. You can solve or find the solutions to any quadratic equation by using the quadratic formula. So it's a really, really nice formula. It's a nice package deal right there. So let's start by finding the zeros by factoring. We got some practice with this in the last section. Now we're going to leverage it to find the zeros of these functions. So here is a quadratic function, and we're going to find the zeros by factoring. This is one that I do want you to try on your own, all right? So we'll jump right into some interactivity here. Think about it for a second. Think how you might factor this. All right. Now, as always, you got to say something out loud. Doesn't have to be anybody. It's even better if you're watching this with somebody and maybe doing the work together. Best case scenario there. But even if not, just say anything out loud to give your brain that feedback. All right. Okay. And now try to work it out. Factor this quadratic expression here, set it equal to zero, and then find the values of x that'll make it equal to zero. All right, here we go. Let's do it together. All right, so first, this is the factoring step. How you choose to factor it is kind of up to you. You can use factoring by grouping, which we talked about in the previous section, or you can just use guess and check. If you're lucky, guess and check might not take too long. It kind of depends on the, the style of these two numbers here. If they're prime, you don't really have a lot to check. You can kind of guess right away. So if we factor this expression like so, then we can set it equal to zero, and this is going to allow us to solve for x, right? Remember, this is why we like factoring, because it makes solving these types of equations really easy via the zero product property. So the zero product property or zero product principle guarantees that this equals zero or this equals zero or both, right? So we set each one of those factors equal to zero and then individually solve for x. And we have our two solutions. So f of x will equal zero when x is negative 5/2 and x is 1/3. And that's how you do it by factoring. Not too bad, right? let's do another one here. And this is where the factorization is going to come in. Factorization domain is going to be important. I want you to find the zeros of this quadratic function by factoring it over R, okay? So maybe you have to think for a second, maybe remind yourself what that means to factor over the real numbers, okay? And try to say that out loud. What does it mean to factor over the real numbers? Right. And now work it out. Find the zeros of that function where you are factoring the expression over the real numbers. Okay, now let's do it together. So remember that because we're factoring over R, irrational numbers are allowed to be some of our numbers. They're allowed to be the constants involved in this expression. Now, one thing that's really handy to notice is that this is actually a difference of squares. That's a difference of squares, and so we can factor it using that special factor form that we learned in the previous section. You just got to realize this is x squared, and this is the square root of 12 squared, just as I've expressed right here. Now that we have it written in that difference of squares form, we can just use the immediate factor form and get this. X minus root 12, x plus root 12. Now the zero product property yields that the zeros of this function are plus or minus root 12. This is why factorization domains are handy. Now, maybe some of you saw a different way to do this. So let's talk about doing it by just solving it using inverse operations. So you could set this equal to 0 and solve it directly for x. So try to isolate x, right? So we're going to add 12 to both sides and get this. Now we're going to take the square root of both sides, but remember, anytime you take a square root, you must include a plus minus, okay? Every single time. If you're ever wondering like, oh man, do I need to include a plus minus? The answer is always yes. If you ever find yourself ever taking the square root of something, yes, you need to include a plus minus. And then, depending on the context, you might be able to eliminate one of those cases, the minus or the plus. In this scenario, we actually need both. And that's why it's important to have the plus minus. Maybe geometrically, I could motivate this a little geometrically for a second. Let me draw a quick boop like this, quick XY plane. All right, so think geometrically about what this is going to look like. And we're going to explore it even more in the next section. But this is basically a parabola shifted down by 12. So you should remember what a parabola looks like. It's roughly like this, very roughly like that. It's been shifted down. So this value right here is negative 12. And what we just found were the x-intercepts of this graph. We found this point and this point right here. And this point is negative root 12, and this point is positive root 12. There we go. So this is why the plus minus is important. You always include a plus minus, and then depending on the context, you might be able to eliminate one of those cases. That's the idea. Okay, now let's shift gears a bit and let's revisit completing the square. Earlier in the course, we learned how to complete the square on quadratic expressions of this form and this form. And the big idea was you had to add zero in a clever way, right? You had to add a clever zero. And the way that we did that was we took this number here, b, divided it by 2, squared it, then we added and subtracted that value to the expression. And then that made part of the expression a perfect square trinomial, which we could then factor using that special factor form. So now what we're going to do is we're going to extend that process to work for any general quadratic expression. The difference here is that we have a coefficient of a here, and that coefficient gets in the way a little bit. So we're going to figure out how to deal with it and then complete the square after we deal with it. Now, a couple just reminders. One, remember, we can complete the square on any quadratic expression. That's an important result. If you got a quadratic expression, you can complete the square on it, all right? The other thing is this, and I just want to re-emphasize this, completing the square is an expression manipulation. It's not an equation manipulation. So you might be tempted to make this an equation and manipulate it, but I encourage you not to. I encourage you to keep it as an expression and then bring the equation in when the context is right. So this is a situation where a helpful application of completing the square is solving quadratic equations, right? But at its core, completing the square has nothing to do with equations. It's just that we can leverage it to help us solve equations when the situation arises. So let me go through how we're going to do this. I'll walk you through this first one, and then I'll let you do the next example. So we're going to complete the square on this expression here, and let me explain how to do it. So in this case, we've got a leading coefficient of 2, and that leading coefficient is kind of in the way. If it weren't there, then we would know how to complete the square on what remains, right? So what we're going to do is we're going to deal with that 2. We're going to ignore the plus 5 all the way until the end. This guy is always just hanging outside the entire time. So the first thing we do is we're going to factor the leading coefficient 2 out of the first 2 terms. So this is going to become this. You see, I factored 2 out of 2x squared, and I factored 2 out of 8x. Right now, what we're going to do is what we already did. So we've kind of finished what we needed to learn. We're going to complete the square on the expression in parentheses. This is why I say parentheses are your friends. They help keep you focused. They group everything. Do the same thing you did before to complete the square here. And there's only one tiny detail we have to address. So what do we need to add and subtract? First of all, we're going to take this number, divide it by 2, square it, and that's what we're going to add and subtract inside the parentheses here. So 4 divided by 2 squared is 2 squared, which is 4. So in here, we're going to add and subtract 4. We're going to add 0, right? So here we go. Here I'm adding 0 in a clever way. I'm going to add 4 and subtract 4. Now, the great part is this. This expression, that is a perfect square trinomial, so we can factor it using those factor forms. However, there's something else. We've got this little -4 that's kind of in the way, right? So we want to get that -4 out of the way. So what we're going to do is we're going to pull it out of the parentheses, but remember, this 2 here applies to everything in those parentheses. So we can't just move 4 out of the outside or to the outside like that without it getting hit by this 2. So when we pull the -4 out, we're going to multiply it by 2. Number 5 is just hanging out the whole time, right? That's just staying the whole time. Don't worry about 5 until the very last step. But we pulled this 4 out, we multiplied it by 2 as we did, and now we can finish the process. So this is our perfect square trinomial. It's isolated. We can factor it as a perfect square trinomial, right? Remember, this number here is always going to be b over 2 by construction. Now, -4 times 2 is -8. And now we can simplify the constant term at the end, and voila, it's done. We just completed the square on a quadratic expression where there's a leading coefficient now. And that's the idea. So let me kind of recover everything I did. You factor the leading coefficient out of the first 2 terms. Then you focus all of your attention to what's in the parentheses and you just complete the square on what's in the parentheses. We add and subtract that special number. Then to get this extra bit out, we're going to move it out of the parentheses, multiplying it by the leading coefficient. Then this will be an isolated perfect square trinomial, which we factor. And then we clean things up at the end, combine the constant terms into one, and we get this. Okay, that is the process. So now that you've seen it, I want you to try it on this one, all right? And let me just say this first. Well, think about it for a second. Stare at it, look at it, ponder it. Okay. Now I want you to say something out loud about maybe what you would do first. What would you do first thing if you had to complete the square on this? Right. And now I want you to try to work it out on your own, but let me give you a little word of caution. The calculations may get a little bit messy because there are fractions involved, but don't fret, okay? Don't let that overwhelm you. Remember, just take a deep breath and write it out. Remember, we control the math does not control us. We are in charge. We just have to follow our nose and go step by step. Oh, and always write your calculations in an orderly way so that you can trace what you're doing. All right, you try it and we'll do it together in just a moment. All right, let's do this. So, We're going to factor the leading coefficient out of the first two terms. And that's where you should first feel that maybe like a little twinge of anxiety, because when we do that, we're going to end up with a fraction as our coefficient right here. That's okay. That's okay. We can complete the square on any quadratic expression, any of them. It doesn't matter what these numbers are. So when we factor 3 out of 3x squared, we get x squared. When we factor 3 out of 5, we get 5/3. And if you want to check, you can always distribute this back to those two terms, and you'll see that you actually get this again. Now, nothing else has changed except the fact that this is a fraction. The process is entirely identical to what we did before. So we're going to take this number, divide it by 2, and square that result. So 5/3 divided by 2, that's half of 5/3, so that's 5/6. Now we're going to square that. And remember, properties of exponents will allow us to square the top and square the bottom just like that. So we're going to get 25/36, right? Now, this may look a little messy, but again, don't let it overwhelm you. That is the special number that we're going to add and subtract. And we're just going to add and subtract that inside the parentheses. Here we go. Adding it, subtracting it, and now we're really, really close. As bizarre as this looks, that is a perfect square trinomial. Maybe a messy one, but it is a perfect square trinomial. Just like before, this term here is kind of in the way. We need to kick this term out of the party. And when we do, the 3 kicks it on the way out, right? So we're going to take this and multiply it by 3 as we pull it out. And so we get negative 25/36 times 3. Now we've isolated that perfect square trinomial and we can factor it by construction, right? So here is where understanding that process of completing the square can really save you. You don't need to try to factor this by hand anymore. Remember, with completing the square, we reverse engineered this structure to be exactly what we wanted it to be. You just got to remember that this term is always going to be b/2, right? So here, I'm not actually manually factoring to go from this step to this step. I'm just remembering that the process of completing the square means this is going to be x plus b/2. So this is our b/2, and that's it. So we don't need to do anything crazy to try to get to this step. All right, now we multiplied this by 3. We could do a little simplification here, right? There's a 36 is 3 times 12, so we can actually cancel that. Let me write this. 36 is 3 times 12. So we'll be able to cancel those threes, and we're just left with a 12 in the denominator, right? Now we're going to combine like terms at the end, right? We can write 1 as 12/12, just like we talked about back in, oh geez, what was it, section 1.6? You can write 1 as 12/12. And so then you end up with 12/12. Well, negative 25 plus 12 is negative 13. So we get negative 13/12. And we're done. Boom. Right. So that is the process of completing the square on any general quadratic expression, all right? We can do it on any quadratic expression. Sometimes it gets a little messy. We're going to see it get a little messy again in a minute, but you know what? That's okay. Sometimes life is messy like that. Right. So now that we know how to complete the square on these things, let's use that technique to find the zeros of this quadratic function right here. So we're going to find the zeros of this function by completing the square. And I want you to try this one on your own. We actually, well, I'll give you this hint before we even start. We already completed the square on this in example 3, I think it was, right? So that's my little hint. Think first about what you're going to do. Okay. Now, got to say something out loud. What are you going to do? Maybe the first step, maybe the last step, anything out loud to give your brain that feedback. Right? Now work it out. Find the zeros of that function using the completed square form. Right. Now let's do it together. So in a previous example, come on, there we go. We already completed the square on this, and we got this as the form where the square was completed. So finding the zeros of f of x means finding the roots of this equation here. So we're going to set our output equal to 0. There it is. And now we can just solve for x. One of the beauties of completing the square, as we're going to see later as well, is it reduces the number of times your variable appears. So, quick little side note here. Notice in the original expression, the variable x appears twice. And in order to solve for x, we need x to be isolated by itself. So we need to reduce the number of times we see x appear. That is what completing the square allows us to do on a quadratic expression. Now, x only appears once. We just need to move everything away from x and we'll be able to solve for x. So here we go. Add 3 to both sides, divide both sides by 2. Now we're going to take the square root of both sides, right? But remember, anytime you take a square root, you have to include a plus minus every single time. So we included the plus minus here. Oops. Now we have x plus 2 equals plus or minus the square root of 3 over 2. We're going to subtract 2 from both sides, and we have our solutions. There's our two solutions right there. Boom. So the zeros of our function f of x are x equals -2 minus root 3 over 2 and -2 plus root 3 over 2. And like I had mentioned before, graphically, what's happening is these are where the parabola crosses the x-axis. That's the geometric interpretation, right? Remember, algebra and geometry, best friends forever and ever. If we're doing something algebraic, there's usually a geometric interpretation too. So you want to get comfortable passing in between both of those because they are equivalent and they can really help build our intuition and just give us a more meaningful understanding of what we're doing and why we even care. All right? So that's what we just found. Now, want to talk a little bit more about completing the square here. And I know I've said this a couple of times already, but completing the square works on any quadratic expression. And well, that means that we could use this process to find a general formula for the solutions of any quadratic equation of this form, right? Think about that for a second. Think about that. What is he saying? He's saying we can complete the square on any quadratic expression. So that means we could find a general form for the solutions of this equation using that technique and using this process that we saw in the previous example. We just need to complete the square on this expression here. That's what we're going to do. All right. So here things are going to get a little bit messy. So let's stretch a little bit. Okay. This is where the math gets heavy, but not as bad as you might think. Just follow your nose, go step by step, walk carefully, and we will get there. So we're starting with this expression here. We're going to complete the square on it using that same technique we just learned. Remember the first step of that technique? Factoring the leading coefficient out of these first two terms. Let's do it. Here it is. That leaves us with x squared, and this becomes b over a. Now we're going to complete the square on this expression in parentheses. So what do we need to do? We need to take this coefficient here. We need to divide it by 2, square it, and then we're going to add it and subtract it, right? That's that special number. So this divided by 2 is b over 2a. And then we need to square that. So we're going to square it, and we're going to add it and subtract it as well. So we've added 0. We haven't changed the value of the expression. It just looks a little bit messy, but that's okay. We can do this. Now, we almost have a perfect square trinomial isolated. Might look a little messy, but that's all right. However, this guy right here is in the way. We need this out of the parentheses. We need this guy out of the party. So when we pull this out of the parentheses, it's going to get hit by this A, right? It's going to get hit by that A, just like we saw a moment ago when only numbers were involved, right? Or just regular numbers, not everything being letters. So when we pull this out, it's going to get multiplied by A. There we go. Oops, too much. There we go. And now this, as messy as it looks, that is our perfect square trinomial. So we know how it's going to factor. It's that standard factor form. It's going to be this, x plus b over 2a squared. Now we can simplify this a little bit, right? So this will be b squared in the top, and this will become 4a squared, but we can cancel one of those a's. So we're just left with b squared over 4a, right? And then the C, remember the C just hangs out a long time. Don't worry about the C until we really have to deal with it, right? So what I'm going to do now is deal with that C because I've got a couple of terms here and I would like to merge them into a single term, just like we did in the previous examples, right? Remember, let me flash back for a sec. Where was it? Where was it? This one, right? Remember, this is the step where we combined this little extra term and this original C term. We're going to do that right now, just like so. We're going to combine these by finding a common denominator and then writing them over the common denominator. So here it is. There we go. Now, this step might look a little bit weird because you'll notice this changes from a positive to a negative. That's because this negative sign is going to apply to the entire expression, right? The entire expression. So it's negative b squared, negative negative 4ac, which gives us a positive. That's why it looks that way, okay? I wanted to keep this sign the way it is. Oof. Man, I feel like I need a break. We're going to keep going. So we're making progress. We're going to continue on the next page. Maybe some of you are starting to recognize some of these pieces. They might look a little bit familiar. So let's continue on. We're going to add b squared minus 4ac over 4a to both sides. Flashback. It's basically taking this and moving it over here, making it positive. So there we go. Now we're going to keep going. Remember, what was our goal? Oh, to solve for x. We need to solve for x. So I'm going to divide both sides by a. This a is gone. Now we have an extra a down here, so that's a squared. Okay. Now we need to take the square root of both sides. Got to include the plus minus. So we take the square root, take the square root. This is what's left on the left side. Now we have plus or minus this on the right side. Maybe it's looking even a little more familiar now. Now we're going to subtract b over 2a from both sides to get that. And then I'm going to distribute or maybe split up this radical between the numerator and the denominator, like so. So now we're going to end up with this in the top. And then this we can simplify the square root of 4a squared. That's just going to be 2a. And then lo and behold, we have our solutions. We have our solutions. Now, maybe now that this is written out, maybe this looks familiar to some of you. This little formula down here, this is called the quadratic formula. All right. This is the formula that maybe was was beaten into your head when you had to learn it before. It's a very, very helpful formula. It gives us the solutions to this equation, right? So x is negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, just like that. Or in other words, if you want to find the zeros of this quadratic function, that is what this formula gives you. That is what it gives you. The quadratic formula just tells you what the solutions are going to be in one step. You've just got to go through and plug in A, B, and C. All right. So here's one where you got to ponder it for a minute. So I'm going to throw up the thinker here. Just look at this formula, think about it, look at its structure. Okay. And here's a time where I want you to say it out loud. Just read the formula out loud to yourself a couple of times so that it sticks. Okay. Now, let me be very clear about this. This is a formula that you do need to memorize. You need to have the quadratic formula memorized. It's an important formula because it gives us the solution to a quadratic equation, or it gives us the zeros of a quadratic function. So you do need to memorize it. A little note that I'll say here, you might have seen this given in a different form where this was written as a single fraction. That is still valid. If you want to do it that way, you can. The reason that I'm or pulling it apart like this is because it has more geometric significance this way. We're going to see why, or I should say, we're going to see what this term really represents, and we're going to see what this term really represents, and we're going to see how this particular structure, where it's written like this as two terms, reinforces what we learn about complex numbers, okay? So that is why it's written in this form. So I'll encourage you to write it in this form so that you can carry the geometric intuition with you that we're really going to get in the next section. All right, now we know the quadratic formula. Let's find some zeros using the quadratic formula. So find the zeros, if there are any, of this quadratic function. And this is the time when I want you to use the quadratic formula. So maybe I'll say this, can you remember the quadratic formula already? And if you can, say it out loud. Repeat the quadratic formula out loud to yourself. Okay. And now use it. So use the quadratic formula to find the zeros of this quadratic function, and we'll do it together in a minute. Right, here we go. So the good thing about the quadratic formula is it's really just a plug and play kind of tool. We just need to plug in A, B, and C and compute. That's it. Ripe for a computer to do even. So remember, the quadratic formula will give us the solutions of this equation. So here, A is equal to 3, B is equal to -5, C is equal to 1, and now we just plug and work. Here we go. Plugged in B, plugged in A, plugged in, oops, sorry, plugged in B, plugged in A and C. They're all plugged in, and now we just simplify. Again, parentheses are your friends. I strongly encourage you to use parentheses here. Beware of writing things like this because -5 squared is not the same as -5 squared. So use parentheses to your advantage, okay? Simplify, let's see, 25 minus 12, that's 13. So we have 5/6 plus or minus square root of 13 over 6. And those are the zeros. Those are the zeros of f of x. All right, let's take a look at the picture in this case. In this case, the zeros are actually real numbers. We'll talk about imaginary numbers more in this section and then in section 3.6. But we got two real solutions to this equation, the zero equation of f of x, right? So graphically, these are where the x-intercepts are for this parabola, okay? And here you can see why I've chosen to represent the quadratic formula in this structure because this is the number 5/6. And then what we're doing is we're basically moving up by root 13 over 6, and we're moving down by root 13 over 6 to get those two x-intercepts right there. Those are the x-intercepts. So I'll discuss this more generally in the next section, but this part of the quadratic formula basically gives you how far to move left and right from the axis of symmetry of the parabola. That's really what it's telling you to do. All right, cool stuff. Very cool stuff. So now we're going to talk about the discriminant in a second. So a quadratic function may have real zeros, meaning real number zeros, or it may have imaginary zeros. That's the case when the radicand of the quadratic formula becomes negative. So you'll end up with what are called imaginary zeros in that situation. It really just depends on what number system we're working in. So in the real number system, R, a quadratic function may have 0, 1, or 2 real zeros. So if you're restricting yourself to the real numbers, there are only those three possibilities. No real zeros, one real zero, or two real zeros. That's it. Only those three cases. Now, if we're working in the complex number system, then a quadratic function will always have at least one complex zero. And that it could be imaginary or it could be real. So this is another situation where the complex number system is a little more robust. It picks up a little more information than the real number system does. So if you're allowing yourself to, frankly, work or factor over C, you're guaranteed that a quadratic function will have at least one zero every single time. Um, oh, sorry, this should say 3.6, my bad. So we're going to have a full exploration of the complex numbers in section 3.6. But for now, just know that they are there, they exist, and we'll go into great detail about them in 3.6. Okay. Now, this is where we talk about the discriminant. So the quadratic formula itself contains an important embedded structure called the discriminant. And the discriminant lets us identify and classify the zeros of a quadratic function. So it also tells us that it'll let us know if our function was factorable over the integers or not. So this is a way of kind of checking if you even want to bother with factoring to begin with, because if you have to factor over the real numbers, it can get kind of messy, and you can get lost in your thoughts really easily. So the discriminant also tells us if you could factor this over the integers or not, right? So it's good to check this discriminant. So what is this thing? What is the discriminant? So if we're given a quadratic polynomial, ax squared plus bx plus c, then the discriminant is this quantity, b squared minus 4ac. This is another formula that you do want to memorize. This is a very, very helpful structure. And what is the discriminant? It's just the radicand of the square root in the quadratic formula. So here's the quadratic formula. The discriminant is just the stuff inside the radical right there. That's what it is. And that this this thing here, that formula, this expression tells us everything we need to know about the quantity and type of zeros that we're going to get. That's why it's so nice. Okay. Um, wait, wait, did I skip it? No. Oh yeah, yeah, okay. So, oh, this is what I just said out loud. Given a quadratic equation, the number and type of solutions depends on the sign of the discriminant here. More precisely, we have these cases. All right. If the discriminant is positive, then your equation will have two distinct real solutions. Okay? Positive discriminant means you've got two distinct real solutions. We'll see why in a moment. If your discriminant is equal to zero, then you will have one repeated real solution. Okay? So if that thing zeroes out, you're going to have one solution. It's going to be real and it's going to be repeated. Then, if the discriminant is negative, you're going to have two distinct imaginary solutions. So that's the situation where you're trying to take the square root of a negative number. Now you're entering the realm of the complex numbers. So if your discriminant is negative, you'll still have two distinct solutions, but they're going to be imaginary. So imaginary numbers will be involved. Right. Now, I'm not the kind of person who just likes to say, okay, this is how it is. Let's dig into why this is the case and why this works. So let's look at the first case. If your discriminant is positive, look at what happens to the quadratic formula. There's a plus minus in that formula, and that means you're going to have two distinct solutions. B squared minus 4ac could be any positive number. 2, 1, 2, 3, pi, e, log of 18. It could be anything, right? But whatever this thing is, if it's positive, then this plus minus is going to give you two distinct real solutions. Geometrically, that means you're going to have two x-intercepts for your parabola, all right? Now, check this out. If your discriminant is equal to zero, then that essentially wipes out the second term in the quadratic formula. So if this thing is zero, like so, well, square root of zero is zero. Zero divided by 2a is zero. And so this whole term gets wiped out, and you're just left with negative b over 2a, right? This is another reason why it's kind of handy to express the quadratic formula like this, instead of mushing everything together over one fraction, over a single denominator, right? So if this is zero, this whole term disappears, and you're just left with this one real solution, and it will actually be repeated. We'll see geometrically what that is more in the next section, but maybe, spoiler alert, it's going to be the vertex of the parabola. That's what happens. Now, if it's negative, then that square root will not disappear, but you're going to be taking the square root of a negative number. And so if you try to take the square root of a negative number, you're now dealing with imaginary numbers, right? So the plus minus still gives us two distinct results. And the fact that this thing is negative means they'll be imaginary. So those are the three cases, and that's why the discriminant is so helpful. Now, as a corollary to that proposition, there's this. This is what's really nice, or something else that's really nice. If the discriminant of a quadratic function is a perfect square, then that means that the formula, the function itself, can be factored over the integers. So the discriminant is helpful to check. If you calculate the discriminant and you find that it's a perfect square, like 1, 4, 9, 16, 25, then that means you could just factor the formula for the function over the integers. You could just factor it. So that can save you some work. Maybe you don't need to use the quadratic formula. You can just factor it with guess and check or something like that. All right. So now, wait, did I? I should have made this one a pause. Okay, pretend you can't see this stuff at the bottom for a second. Okay, where's my, okay. Yes, so pretend you can't see any of this stuff. Okay, avert your eyes, avert your eyes. Consider this quadratic function here. I want you to compute the discriminant and then see what it tells you for a second. We're going to do this again in a minute too. All right, go ahead. All right. Okay, you got it. All right, so looking at this quadratic function, the discriminant, b squared minus 4ac, is this. 1 squared minus 4 times a times c. Parentheses are your friends. So simplifying this, we get 1 plus 24, which is 25. That is a perfect square. So because this thing is a perfect square, that means this can be factored over the integers. Remember, that just means we can factor it using integers only. There won't be irrational numbers involved or imaginary numbers involved. Everything is going to be an integer here. So you can factor it using factoring by grouping, using guess and check. And when you do, you get this. Now you can find the zeros using the zero product principle. Yeah. Okay. Now here's one for real. I want you to find how many zeros this function has and what type they are, and then what the zeros are themselves. Okay. So this one you'll work on your own. So think about it for a moment. Okay. Now give your brain some audio feedback. Say out loud what you might try. Maybe what you'll try first. Okay. And then work it out on your own. How many zeros are there? What type are they? And what are the actual zeros? And we'll do it together in a moment. Okay, here we go. So if we want to know how many zeros they are and what type they are, we need to compute the discriminant. So let's start with that. The discriminant is b squared minus 4 times a times c. Again, parentheses are your friends. Make sure to use them. Simplifying, we're going to get 16 minus 24, which is negative 8. That's a negative number. So automatically I know that there's going to be two solutions and they're going to be imaginary. There's two distinct imaginary zeros of this function. We'll see more in the next section, but geometrically that means the parabola doesn't cross the x-axis because our solutions, our zeros, are not real. We'll see why in the next section. So we can still compute them. And here's the beauty of computing the discriminant in advance. If you've computed the discriminant already, then half your work in computing the quadratic formula is done. You kind of did the messy part already. You already computed this radicand, so use it, right? This is going to be square root of negative 8. What we're going to see when we talk about imaginary numbers is that you can write this as I times the square root of 8. Maybe you've already seen this before in a previous class. Then we're going to simplify. So negative 4 over 6 is 2/3. We can simplify this radical a little bit. We'll talk more about that in section 4.1. And we can write it as 2 root 2. Then we can cancel this 2 and the 2 in that 6 and get a 3, and we're left with this. So our two solutions are 2/3 plus or minus I times root 2 over 3. Two imaginary solutions. All right. And on that note, on that note, let's play. Again, as always, I am excited to work with you all about this. Your instructor is excited to work with you all on these things. These ideas are really important. We're still just focusing on quadratics for now. We haven't gotten to general polynomials, but we're building up to it throughout this whole chapter, okay? So we're going to talk more about quadratics in the next section. We're going to look at the geometry. We're going to look at parabolas, talk about the vertices, axis of symmetry, all that stuff in the next section. So until then, Thank you all for listening, and I will see you next time.